Okay, I think we should start now. It's 3 o'clock now. Okay. So that's just to continue about what we discussed about the convergence of Fourier sequence. Okay, of the convergence of Fourier series. And last time, as we mentioned, if we do want some kind of sequence of functions converge to another function, when you have this kind of sequence of functions, it's a convolution of some kernels. If you want this kind of convergence, which will to be at least a uniform convergent, then what you need is this kernel you want is good kernel, so-called a good kernel. Okay. However, for the Fourier sequence, the partial sum of the Fourier sequence has a Dirichlet kernel which is not a good kernel. Okay. And the reason why the Dirichlet kernel is not a good kernel is simply because, well, the Dirichlet kernel is just like this picture. Okay, the function is just like this, although it's decaying, but it's oscillate a lot. Okay, so which means if you take F's value, if you flip everything below the x-axis, and then what happens is this dn is a very big function. Okay, and then we cannot really say that this Fourier series converges to functions whenever this function is continuous, but we have something instead, right? We have, first thing is, well, if this function f is twice differentiable, continuously differentiable, then we have this, as n of f converges to f, simply because the Fourier coefficient of this function f is of order 1 over n squared, which is something that absolute convergent. Okay, and the second, although we cannot say that the Fourier series converges to f, however, if we do some other means of this Fourier series, which is so-called the Cauchy means of some summation or Cauchy summation, then we know that the Dirichlet kernel will somehow change to, by averaging, it can change to so-called the Fourier kernel. Okay, and this Fourier kernel, instead of this Dirichlet kernel, is a good kernel. Okay, so then that means we are able to guarantee that the Fourier kernel convolved with f converge to f whenever f is continuous. And if f is continuous everywhere, and this convergent is uniform convergent. Okay, and a direct corollary is this function, for any continuous function, it can be approximated uniformly by the trigonometry polynomials. Okay, this is something we mentioned last time. And any question about this part? Any question before we move on?
But wait, so this Fn was basically a kernel what we get after we do Abell summation, right? And so it's not like approximating. Wait, so it approximates f, but if we take means of the series, right?
Yes, that's right. We take some kind of means of the series, not really the Fourier series, but some other kind of series, and then this kind of series can approximate f uniformly if f is continuous. Okay. And this series, the only thing we know is, okay, it's not a Fourier series. It's not directly the Fourier series, but it's actually some kind of trigonometry polynomial. Okay. It's just like, well, if you have learned this analysis, it's just like if you try to make the Taylor series to approximate your function. This may not work, right? The Taylor series, it may approximate to your functions, but in general, it may not. It may not converge. The Taylor series of a function may not converge to the function itself. However, if you try to search Wiki or Google, and the so-called the name is so-called Legendre polynomials, you will find that this kind of Legendre polynomials, if you try to make some linear combination of the Legendre polynomial, it can approximate to arbitrary function. Okay. So which means, although you cannot really use this kind of x to the power n, this kind of linear combination of x to the power n to approximate your function, you cannot really use cosine n theta, sine n theta to approximate function f. But if you try to change this kind of functions, if you try to change this x to the power n to some other polynomial and do the linear combination, it can approximate to your function. If you try to do some other kind of trigonometry polynomials, then it can approximate to your function f. Okay. Any question? Any other question?
Okay, so just to be sure, initially we wanted something to be convergent if we just take a polynomial, but then it didn't work out. So now we're aiming for a lower aim, just like let's just have any kind of trigonometric polynomial will be satisfied with it.
That's right. So which sounds quite incredible, but it is true. Okay, so you can try to change your polynomial to some very complicated polynomial, and then this kind of polynomial, instead of this very trivial polynomial, can approximate to your function. Okay, this is also so-called the Stone-Weierstrass theorem. It is a theorem say that any functions can be approximated by polynomial uniformly. Okay. Any other question? Okay, then we say that there is this kind of summation, such that this, although we know that this Fourier series may not convergent, but if you try to take a mean, then it will converge. Okay, now what we're trying to do today is, we will try to take another kind of summation. This is so-called the Abell summation. And you'll find that this kind of summation, although it's even more complicated than Chisello summation, but it can also make your Fourier series and this kind of means of summation converge to F. And then we can use this kind of summation to really solve our problems about the elliptic equation or the Laplace equation on the disk. Okay. So what is the Abell summation, or the Abell means of the sequence of the series? Let's say we have a sequence and we want to take a sum of them. Okay, k from 0 to infinity. And it may not be summable. Okay, this series may diverge. Okay, but then we can somehow change the means of summation in the way of Abell. Okay, it's said to be Abell summable to S if for any R is greater than 0, less than 1, we define AR to be the summation k from 0 to infinity, ck r to the power k. Okay, and then we have a lot of AR. For different R, we have different AR. Okay, and the limit as R goes to 1 minus, which means it approximates R but less than R, this AR equals to S. Which means this AR, if you take R goes to 1, it has a limit. Okay? You can find that if Cn itself is summable, which means this sequence it itself is is convergent, then this R tends to 1 is trivially this this summation is equals to S, right? Because you can just plug in and say that okay, if R equals to 1, then A1 is actually equals to this summation. However, if you see ck is not summable, then this limit exists can somehow also tell you some kind of information about this summation of ck, although the summation of ck it might diverge.
Can I ask a question?
Sure.
No, about the Cesare summation, can you give an example of a sequence that doesn't converge, but then a Cesare sum converges?
Yeah, this sequence is a good example. Say that this sequence is not converged, right? Because you have 1, 0, 1, 0, 1, 0, 1, 0. Jump from 1 to 0. The summation will always jump from 1 to 0, 1 to 0. So this summation will not converge. Okay? However, if you try to take this example is an example we have last time, right? And however, if you take the Cesare summation as we shown last time, it's actually has a limit, and this limit is equals to 1/2. Okay, you can check the lecture notes last time. It's a very interesting example, and it shows that somehow it somehow shows that the Cesare summable is stronger than the summable of a sequence. Okay, so which means if a sequence it converge, then it must be in the Cesare means it converge. However, if a sequence is Cesare means converge, it doesn't mean that the sequence will converge. Okay. I forgot whether we have this the homework assigned to be this kind of thing or not. There is I think there is problems. There is exercise in our instance book, and ask you to show okay, Cesare summable is stronger than it's weaker than summable. Okay, which is a statement I just made. Okay. Any other question? And we have another kind of summable things, right? This is Abell summable. And again, let me show you an example about a sequence that is Abell summable, but it may not be summable in some sense. 1 minus 2 plus 3 minus 4. And so on, which is equals to the summation of -1 to the power k times k plus 1. Okay, this sequence. And if we call this, this AR to be this sequence -1 to the power k, k plus 1 to the power r to the power k, k from 0 to infinity, then you see that this sequence is nothing, or this series is nothing but the antiderivative of r to the power k plus 1, right? if you take the derivative in terms of r of summation minus 1 to the power k, r to the power r plus 1, k plus 1, then what you get is term by term is equals to this. Okay, so which means you could try to, well, by taking the derivative
Well,
of,
I'm sorry, can you explain again what you just said about derivatives? Because I missed it.
of course. Let's say, well, you have a function ax is equals to minus 1 to the power k, k plus 1 to the power x to the power k. Okay, this is one sequence. This is one Taylor series if you want. And let's say you have another series, which is the summation of minus 1 to the power k, x to the power k plus 1. Okay, then what's the relation between these two series? Well, you can see that if we take derivative of the second one and take it term by term, okay, then what we get is the first one. And you are able to take the derivative term by term simply because if x is less than 1, then this convergence, this Taylor series of bx converge uniformly. You can check the radius of convergence of bx. Okay, so which means this b prime of x is equals to minus 1 to the power k, k plus 1, x to the power k, which equals to ax. Okay, and that means, okay, well, what is bx? Bx is very easy to compute because bx is just a geometric series. It's 1 over, well, 1 plus x with minus sign. Okay, then what is your ax? It's just a b prime, right? So ax must be equals to 1 over 1 plus x squared for all x is less than 1. Right? Because the convergent is uniform convergent. So that means if you take the limit as r goes to 1 minus ar, it's just a limit as r goes to 1 minus 1 over 1 plus r squared, which equals to 1/4. Okay, so this is a finite number. So that means this series minus 1 to the power k times k plus 1, this series is actually in the means of Abell, it converge. Okay, however, you can check that this series, it is not a convergent series. It is not even convergent in the means of Chesalo. Okay, you can check yourself. So this simply tells you a hunch that, okay, the Abell summable is the weakest summable. It's the weakest summable. Okay, and if you have a sequence that is Chesalo summable, then you have this sequence is also Abell summable. But if you have a sequence that is Abell summable, it is not. It may not be Chesalo summable. Okay, and in the, well, of course, if you have a sequence that converges, well, in the usual way, then we can conclude that it is also Chesalo summable, but the Chesalo summable doesn't mean the sequence itself is convergent. Okay, so we have a weaker and a weaker ways or means of summable of a sequence. Okay. Any question? Any question? Okay, as I said, this is something maybe I probably will leave it as a homework problems. Abell summation is actually weaker than the Chisato summation. But based on this spirit, that means, well, if you try to take the Abell way, Abell means of summation of Fourier sequence or Fourier series, then what you should get is also something summable, right? Also, you should get something such that it is, it is a very good series. So we can define this way of Fourier series, which is ARF theta, which can be written as, well, the summation of R to the power M and e to the I n theta F hat, let's say this is n, F hat n, and from minus infinity to infinity. This is because you have these two ways of summation, so we need F's value here, but it's just a two sequence, okay? You take a sum of these two sequence. And this would be the Abell means of Fourier series, okay? Or ARF. And then what you can do is, just like what we did before, you can somehow write it as the convolution of F and another kernel, PR theta, where PR theta is equals to the summation n from minus infinity to infinity R to the power n e to the I n theta. Okay? Well, because you see this one is equals to n from minus infinity to infinity R to the power n e to the I n theta, and this is an integral from, well, minus pi to pi e to the minus I n phi f phi d phi. Okay, and you put it inside, and then it becomes the integral of summation of R to the n and e to the I n theta minus phi f phi d phi. Okay, from minus pi to pi, 1 over 2 pi. So of course, this is a convolution with kernel like this. Okay, this is a kernel. Now, you see, we have a kernel, which is like an infinite series, right? However, this infinite series is not so bad. Again, not so bad. And well, the thing is, you can actually, for R less than 1, or R, because R is positive, R is less than 1, greater or equal than 0, you can actually find the explicit expression of this infinite summation, right? You can take from n equals to minus capital N to capital N and this summation, and then take this capital N goes to infinity. After all, it's nothing but a geometric series. Okay, this is nothing but just a geometric series. So you can take the sum, and you will find that the sum is actually equals to 1 minus R over 1 minus 2R cosine theta plus R squared. Okay, by some algebra, which I hope you can do it yourself. This is just an algebra. Okay. So is that's clear that you are able to do this kind of summation? Okay, is that clear? And from 0 to plus infinity, plus, and from, well, minus infinity to 0, then there will be, well, R to the minus 1, e to the I theta to the power n. Okay, and this are both, well, geometric series. So you are able to find the expression for this infinite many sum. Okay, that clear? And then after you do the algebra, you got this one. I don't want to do the algebra. So again, we got another kernel, PR theta, to convolve with F. However, this convolution is slightly different. It is slightly different from what we had before, right? The reason why I say it is slightly different is, well, it's simply because this kind of sequence, what we are interested, it is already an infinite many sums, right? But with what we are interested is when r goes to 1 minus, what happens to this one? Well, if r is something less than 1, then we know that this kind of thing, it converges absolutely, right? This kind of thing, whenever r is less than 1, it always converges because it's for this kind of thing, it's always less or equal than the integral of f times r to the power n, right? So this kind of sequence, if r is less than 1, it's always converge. And this converge is almost uniformly, but it's not really because well, we can take r closer and closer to 1. So the only problem now is whether we can take r tends to 1 minus and then this kind of thing tends to f or not. Okay, so and before, what we're trying to say is what happens if you have Fn convolve with f and whether it tends to f or not as n goes to infinity. But now the problems are slightly different, which is we want to see this kernel convolve with f, whether it converts to f or not as r goes to 1 minus. Okay, this becomes a slightly different problem. But well, after all, it's almost the same thing because it's just something like change from n goes to infinity to r tends to 1 minus. Okay, and as I mentioned before, you already have this kind of convergent. This is Chasalo means of convergence. So you should have this Abell means of convergence. Okay. By the way, this PR of theta, it has a name. It's so-called the Poisson kernel. Okay, this function is so-called a Poisson kernel. And if you want to say that, if you want to say this kind of convolution converges to f, we only need one lemma, which says that this kernel, this Poisson kernel, is, with the same spirit, a good kernel. Okay? You see, the parameter here is r instead of n. Okay? So what does that mean? What does that mean to say this kernel is a good kernel as r tends to 1 instead of n goes to infinity? Well, the definition is almost the same as before. We have for, well, good kernel in this way means first you have this PR of theta. If you take the integral from minus pi to pi, d theta 1 over 2 pi is equals to 1. Okay, and the PR of theta with f's value, d theta from minus pi to pi is bounded above. Okay, the third thing is slightly different. That is, if you take the if you take the integral for theta, it's away from 0. It's away from 0, from delta to pi. PR of theta d theta tends to 0 as r goes to 1 minus. Okay? You can see that it's slightly different. The reason why it's slightly different is very easy to see. For this function, you can see that it is singular. It is singular when cosine theta equals to 1, right? If cosine theta equals to 1, then r could equals to 0 if r equals to 1. Okay, so that's the only bad point when theta equals to 0 and r equals to 1. This is the only bad point. So if we exclude it, then everything is perfectly good. Okay.
Wait,
And,
sorry, what happens when theta equals to 0 or equals to 1?
well, if theta is equals to 0, right? If theta is very close to 0 and r is very close to 1, then this PR theta will goes to infinity. Right? Because your denominator equals to 0.
Oh, okay.
Right? So, which means it has, again, it's just like the good kernel as we mentioned before. If r is very, very close to 1, okay, then all the dense or all the mass will concentrate on theta equals to 0. It will somehow very concentrated on theta equals to 0 for this kernel. Which is why if you take this kind of average, this f will, this averaging of this f will converge to f. Which you can prove it rigorously, but this is really almost the same as what we did before, so I will not do it again here. The only thing I want to say a little bit is, well, why this PR theta is a good kernel. The first thing is for sure, right? The first thing is for sure because if you take the integral of this PR theta, you'll find that the only thing that left would be Rn equals to 0. So the integral of the PR theta d theta is just a 1. Okay? And the second one, well, PR theta is actually a positive number. It's a positive function. And the third one, well, you can show it by saying that if theta is away from 0, then the denominator, whatever r you have, is away from 0. This is 1, this is 2, this is 3. And 1 and 2 are trivial, but 3 will for theta is greater than delta, less than pi. We have this 1 minus 2r cosine theta plus r squared is greater or equal than some constant, C delta, which is greater than 0. Okay? And this C delta, it doesn't depend on R. Because R, whatever R you have, is always greater or equal than C delta, which is something, well, for instance, this cosine theta is always greater, well, less or equal than cosine delta. So 1 plus r squared minus 2r is always greater or equal than something, which is, well, positive. And for r is greater than 1/2, less than 1. Okay, so that means PR theta is less or equal than 1 minus r squared divided by C delta. And this, if you take the integral both sides, this on this right-hand side, it tends to 0. Greater than delta, less than pi is, well, on the right-hand side, it's less than 2 pi, 1 minus r squared divided by C delta tends to 0 as r goes to 1 minus. Okay? So this is a good kernel. And by the same way as we deal with the good kernel as before, you can show that this PR theta convolve with F converge to F whenever F is continuous. Okay. And this gives us a very good result in order to deal with the Laplace equation on the disk, okay, which is a theorem. Let's say F is a integrable function on the unit circle. Say, then we call this UR theta to be F convolved with PR theta. Okay? This function is satisfying the following three properties. First, even if F is only an integrable function, but U has has a second continuous derivative or two continuous derivative in the unit disk. In the unit disk, which you can see, okay, what we claimed before, right? PR is kind of something very smooth and F is only integrable. Then the convolution of F and PR is twice differentiable. It's actually smooth. It's actually, you can take arbitrary differentiation on this function. It's smooth, okay? And the Laplace of U equals to 0. Okay, so it satisfies the Laplace equation.
Oh, wait, sorry, why doesn't it satisfy a Laplace equation?
Well, that's something we mentioned a long time ago, maybe last week this time. Okay, last Tuesday, which is how we can solve the Laplace equation on the unit disk. Well, we solve the Laplace equation on the unit disk if U can be expanded as R to the power n with F's value e to the in theta F hat of n. This is something we did before. Okay, you can check the lecture notes last week. And second, if theta is any point of continuity of F, then we know that the limit as R goes to 1 minus UR theta equals to F theta. So which means if F is continuous everywhere, then this limit is uniform. This convergent is uniform convergent. Okay? So which means if you really gave me the initial data on the boundary, on the circle, okay, then suppose this boundary condition is continuous. Then what we have is, well, you do this kind of surgery of your function, you do this kind of convolution of your function, then this function satisfies the Laplace equation. Moreover, if you take the limit, it actually equals to F theta. It's somehow like you are able to plug in R equals to 1. Okay? Which is something you have to ask your solution to be satisfied because that's your initial data, right? That's your initial data, so of course it should satisfy when R equals to 1, it's equals to your, the boundary.
Oh, actually, how do we prove that the limit is uniform?
Well, because it's a good kernel. For a good kernel, the convolution of this good kernel and the function will converge at each point at each point of continuity, and If everywhere is continuous everywhere, which means it's uniform continuous on the whole interval, then this convergent is uniform convergent. Okay, this is some properties about a good kernel. And thirdly, if F is continuous everywhere, then U R theta, this solution is the unique solution. Satisfies 1 and 2. It is the only solution. Satisfy, it is the only function satisfy Laplace U equals to 0, and this limit is equals to F theta. Okay, it is the unique or the only function satisfy these two conditions. So we solve the Laplace equation on the disk rigorously. If we have proved these theorems, okay, if we are able to prove this theorem. So before we prove this theorem, any question? Any question? Then let's try to prove it. Okay, let's first prove 1. Well, for 1, as we mentioned before, U, which equals to the summation R to the power n e to the in theta f hat of theta, well, or an theta, and from minus infinity to infinity. As we shown before, if this kind of function or this kind of series, it converges uniformly, or if you are able to, well, take derivative term by term, then we know that R to the power n e to the in theta an is satisfy Laplace of this function e to the in theta equals to 0. Okay, so if we are able to show some kind of uniform convergent, then we are done, right? If we are able to show that this kind of sequence uniform convergent to U, to a function U, then we are done because the Laplace of this U is equals to 0. So the hard part for part 1, the hardest part for part 1 is how you can show that this U is twice differentiable, or actually is a smooth function. And how can you show that this convergent to U is a uniform convergent? This would be the problem we have. Okay, so let's try to show that. Let's say we fix rho, which is greater than 0. We cannot really show that this sequence, it converges to U uniformly when R is greater than 0, less or equal than 1. Because, well, it is highly possible that when R, well, if you have R is very close to 1, and then this sequence will not converge uniformly. It is highly possible. Otherwise, you know that if it is well, if it is converged uniformly when R is less or equal than 1, then if you take the limit, well, you can plug in R equals to 1, then what you get is, okay, this sequence will converge to F for your integrable F, right? But we say that this Dirichlet kernel is not a good kernel, so which means it shouldn't converge to F when R equals to 1, if you plug in R equals to 1. So which means you do not expect R from 0 to 1, this sequence will converge uniformly. Okay, so what you do expect is something else. you do not want it to converge on the whole range from 0 to 1, but you can somehow make it slightly less than 1. Okay? Let's say for fixed rho greater than 0, maybe very close to 1, we can choose, well, for any r is less than rho less than 1, then this convergence is uniform and absolutely. Why is that? Why, if r is less than rho, this this series will converge to U uniformly and absolutely? Why this series will converge absolutely, and why it converges to U uniformly if you have r is less than rho? Anybody can make comments?
Oh wait, because we know that it's a good kernel, and like the Poisson kernel is a good kernel, so we can try to use some of its properties.
Yes, but you see, this is slightly different. We're discussing about R, right? We're trying to say that because we don't assume this f is continuous function at this moment, right? So kernel may not help us at this moment because we want to show that after you do this convolution, your U is a smooth function. How can we show that? If we want to show that, that means we want to show this convergent is uniform in R and theta, right? This is something we want to show. Now, suppose your R is less than some number which is less than 1. For instance, R is less than 0.9. Then in this case, are you able to show that this convergence is uniform convergent?
We can zoom it to a geometric sequence.
Yes, that's right. It is uniform and absolute convergent simply because r to the power n e to the I n theta f hat of theta, each terms is less than rho to the power n, right? And the rho to the power n is summable. So we know that this series converge uniformly in R and theta. Okay? It's simply because we have something to dominate it. So that it's this is something converge, so this will also converge uniformly. Okay. Well, this converge uniformly, so that, and you know that each terms is a smooth function. It's just r to the power n times e to the I n theta. Well, I'm sorry. It seems that I write something wrong here. It is f hat n. Sorry about that. And each terms are just a smooth function. So since the convergent is uniform convergent, so that means for any r, U of r theta is smooth. R and theta is smooth at r and theta with r not equals to 1.
Oh wait, a question. So when we're saying that Rn E in theta of theta is less than rho in the power of n, that's okay. That's because we basically know that E in the power of in theta would probably be less than 1, so we can
It's
just
1, yeah.
write it. And then Rn is less than rho n, so it's okay. But F hat n. Do we know? Ah, okay. I see.
Right? F hat n is an integral from, well, 1 over 2 pi, from minus pi to pi, f theta e to the I n theta d theta, right? So it's less or equal than, well, if you take absolute value here, then it's less or equal than 1 over 2 pi minus pi to pi f theta.
Yeah, and we know it's bounded, so we can just write
It's
it as
bounded about
pi.
by some constant, right? So here you have a constant here.
Okay, I see.
That's a good catch. Okay. So you got that for any single point, this function is smooth at this single point. If this single point is not on the boundary, it's inside of the boundary. Okay. So we have this U is smooth, or in special, it is twice differentiable. And Laplace U equals to 0 because Laplace of everything just equals to 0. At any point, R theta where R not equals to 1. Okay? That clear? That clear?
Yep, clear.
Okay, now we have the first property. We also need the second property, but you can see that the second property about the convergence of this, this convolution is nothing but the application of good kernels. You can try to run the same argument as we do with the good kernel. No, I'll not do it here again. Okay. Now, the only issue is, how about the third one? Well, the third one, well, you want to show that this solution is a unique solution. Why it is unique? This is something not so clear, at least, it's not so clear if we don't make some argument on it, right? So suppose it's not the unique solution. Suppose there is another one. Another V R theta solves the problem. This is V solves the problem. The problem means Laplace equation with the boundary condition equals to F theta. Okay? Then we know that VR theta, you can do an expansion, Fourier expansion with respect to theta, right? Because VR theta, you can always do the expansion. It is A and R. The coefficient will depend on R, e to the I n theta. And A and R is equals to 1 over 2 pi, from minus pi to pi, V R theta e to the minus I n theta d theta. Okay, and from minus infinity to infinity. Okay, then we know that V satisfy the Laplace equation. What is Laplace equation? Laplace equation is just partial V partial R squared plus 1 over R partial V over partial R. This is your homework problem. I hope everybody can solve it. 1 over R squared partial R partial V squared partial theta squared equals to 0. You have this. And if we multiply e to the I theta, I n theta, well, basically we try to resolve it again and see, okay, eventually it has to be those kind of things. multiply by e to the minus in theta and integral. What we have is an double prime plus 1 over r an prime of r minus n squared over r squared an of r equals to 0. Okay, well, it's just multiply e to the minus in theta. Then, okay, for this term, it's just you take 2 integration by part, which is why you have n squared in front. Okay, or if you want, you can try to look at the Fourier coefficient of these equations, and then, as we mentioned before, take derivative. It's just like multiply by minus in in front. So, which means you will have this n squared. Then, again, by the homework problem of you get an of r is equals to an r to the power n plus bn r to the power minus n. Okay, this is an ODE problem. Oh, for n not equals to 0. And
Wait, I'm
equals
sorry.
Mhm.
Give me a sec. So like, okay, so we get double prime because we take r squared derivative. We get 1 prime because we get, but then when we take double derivative relatively to theta, because of the fundamental theorem of calculus, we get rid of the integral. And then, but how do we take like the second derivative again?
Well, we have VR theta if you take the second derivative here, right? And e to the minus in theta, you take the integral. Then you try to do the integration by parts, then it's this minus in times, again, partial theta v e to the minus in theta, right? So you can do the integration by parts again. Then you will have additional minus in. Then you have minus pi to pi v e to the minus in theta d theta.
And how did we get an back?
Well, this is an, right?
Wait. Oh, that's
This
how
is
we
nothing
define
but
it.
an, right?
Wait, how did we get it by taking 2 derivatives? That's
Well, you
oh,
just buy
it's because we
integration by
integrate
parts
by
twice.
parts and one term just disappears because it's periodic. Okay.
Yes. Mhm. Okay. That okay? Do I get stuck?
No.
Hello? Oh, okay. I thought I got stuck. Okay, it seems no. Okay, so we have this an is equals to this one, right? As we have before. And we have V is bounded because it is solution, so it's well, it's everywhere bounded. It's twice differentiable on the disk, so it's everywhere bounded. Then we know that, well, your an of r is bounded on the, well, on the disk or near the zero, near the origin. Okay, because V is bounded near the origin. V is bounded near the origin because V is a well-defined function near the origin. So an of r is bounded or near the origin, right? So we must have bn equals to 0. Okay. So we have an is equals to 1 over 2 pi minus pi to pi. Well, f theta e to the minus in theta d theta, simply because let r goes to 1 minus, well, the convergence is uniform. So we can plug in. Okay, so which means your coefficient must equals to the Fourier coefficient of your f.
Wait, how do we get it?
Because this convergence, you assume your v satisfy 1 and 2, right? So that means
yeah, my question is not, my question is, how do we get that v is odd?
v is odd. V is not odd. V is bounded near the origin, right?
Oh,
so
that's bounded. Sorry.
Yeah, this is bounded. This is not odd. This is bounded near the origin when r equals to 0. It is bounded. So which means a and r is also bounded when r equals to 0. So which means it cannot have this term. Okay? And since this convergent is uniform convergent, this convergent is uniform convergent, so that means you can plug in r equals to 1 and you still get that. So that will give you an must equals to the Fourier coefficient of f, because f is equals to the summation of an e to the in theta. Okay? So this means v hat n, v hat n, vr hat n. You take the Fourier coefficient with respect to theta, it must equals to ur and theta. And by the uniqueness of our Fourier coefficient, this gives us ur theta equals to vr theta. Okay, let's finish the proof. A very quick remark is, if f is identically equals to 0, what happened? If r is identically 0, what happened?
Do we get that our Fourier coefficients should be 0?
Yes, then that means we only have one solution, right? Because f is continuous everywhere, then you must have the solution is trivial. It's just a 0. You don't have any other stuff. Okay. So this gives us a very nice result saying that, well, actually in general, this could be true. If you have everything is just a trivial, you don't have any source in your PDE. If you do not have any source on your PDE and your boundary condition is 0, then if this PDE is somehow a good PDE, which means the solution is unique, then you should get the solution is 0, right? Which means if you can see that nothing can be put into, well, if there is no arbitrary no source, absolutely no source on your physical experiment, then you should get, okay, the solution or the physical phenomena is everywhere just 0. And there will be no other situation that you need to consider. Okay. So this gives us an answer to the Laplace equation on the unit disk. We've shown that the Laplace equation on a unit disk has a solution if the boundary condition is continuous, has a solution, and it has a unique solution. The existence and uniqueness are well defined for this PDE. Okay, although it's not very easy to get into this point, but we have made it. Okay, let's have a 10 minutes break and we will resume at 14. Okay.
Yay! Oh, by the way, what is the difference between Fourier coefficients and trigonometric series? Because I didn't really find any difference.
Well, the only difference is, well, the trigonometry polynomial is just like an arbitrary polynomial, right? It's just like you have some polynomials, and you also have for a function, you also have the Taylor series, right? It's just Fourier series is and the trigonometry polynomial is just like the Taylor series and the polynomial series.
Wait, what do you mean?
Well, for instance, you may have a function, right? And this function may have some Taylor expansion, x to the power n, right? Then this is a Taylor expansion of f. And you also have this function. It may have some other kind of approximation by something like an Pnx, where Pn is a polynomial. Okay. And you can somehow choose this Pn careful enough such that this sequence can approximate f uniformly. But this you cannot ask for this Taylor expansion. Maybe I should try to find. We still have like 2 minutes. Let me try to see if I'm able to find. Polynomial. Let me share this with you. This. So you could use this kind of polynomial and do this linear combinations and to approximate an arbitrary function. Okay.
Mm-hmm.
And but this convergent could be uniform convergent in some finite domain. But if you want to do that by using the Fourier, well, by using the Taylor's expansion, then it is impossible, right? Because you know that Taylor's expansion, Taylor series may not approximate to your function, may not converge to your function.
Mm-hmm.
So this is a difference. Mm-hmm. And for the Fourier series, it's the same. Fourier series may not converge to your functions. But if you try to play with trigonometry polynomials, you can somehow make some trigonometry polynomials and do the linear combination and approximate your function. Uniform.
Oh, and also in the book they mentioned we can always change an integrable function at one point without changing its Fourier coefficients. Is that just
Yes.
because, is that just because when we integrate we don't really care about changing one point because integral would be the same?
Exactly. Yeah, that's the reason. Because when you take the integral, well, you have one removable point, discontinuity. It doesn't change the value of the integral. Okay, we should go back and try to discuss a little bit more about, since it's very important, about the convergence of a Fourier sequence. Okay, we just discussed about the pointwise convergent and uniform convergent of Fourier coefficient, and you find that if you try to ask what happens for the uniform convergent, or at least a convergent of the Fourier series of a function, then the answer may not be as good as you thought, right? There might be, as I mentioned before, there might be some functions such that this function is continuous, but the Fourier series of this function does not converge to this function. So then we need to discuss a little bit more about in what sense the Fourier coefficient is a very good approximation to a function. In what sense the Fourier coefficient or the Fourier series is a very good thing in order for us to study, okay? This is a little bit more, it's actually discuss something in general concept, okay? It is something that you might use in the future in order to study PDE. Not in this course, but in some advanced PDE course. Okay. This, well, is so-called the mean square convergent of Fourier series, or after you learn the measure theory or the real analysis, you will see what's the meaning of this mean square convergent. It's actually something so-called the L2 convergence of Fourier series. Which, let's call it theorem 1, which is something we're going to prove today, well, which is saying that suppose you only have an integrable function on the circle. And as Anya mentioned, well, of course, we cannot expect the Fourier series will converge to F pointwisely, because you can definitely change the value of F at one point, but all the Fourier coefficient doesn't change at all, right? Because the Fourier coefficient is just an integral. So you do not expect that this Fourier coefficient will converge to F. However, if you take some kind of sum, then it will converge. This F theta minus Sn F theta with square here, d theta, it tends to 0 as n goes to infinity. So although we don't know what happens for F, well, we don't know pointwisely what happens for this Fourier series. But if you take this kind of subtraction with square here, then it will tend to 0. The reason why we have square here is something very interesting, which we will see in a minute, okay? So what we have is, although we don't know pointwisely what happened, but if you have this integral, then it will converge, okay? So I guess the rest of today's lecture we will try to tell you how to prove this theorem, and also some corollary to this theorem. Okay. So before we move on, any question about this theorem?
Sorry, I forgot the notation. SNF is which one?
It's the partial sum of F, of the Fourier series of F. Sn of F is equals to the summation n from minus n to n f hat of n e to the I n theta. Okay, so you only take this partial sum, the truncated sum of the Fourier series. Okay. Well, in order to show this,
and so it means it converges uniformly, right? Because we didn't choose tether.
Well, you see, we don't have a variable here after you take the integration, right? So this convergent is a number. Well, this is a number For different n, it just gives you a different number. So it doesn't make sense if we want to discuss whether it's uniform or not. Because if you want to discuss about uniform convergent, you are discussing this convergent as n goes to infinity, you will have another parameter. Uniform in the sense of that parameter. But for this one, you don't have any other parameters other than capital N. So this convergent is just like a n or some bn tends to 0. This kind of convergence, right?
Yeah, but like also we have different like variables for f. And so
Well, then that will be a very hard problem because for different f, well, you may have different kind of convergence. So this, you can see that is kind of, well, because if you try to see it as for different f, then it is pointwise convergent in this sense. For fixed f, it will always convergent. But for different f, well, this convergent is not uniform.
oh, but like for the
Very
same
big.
f but different theta.
Well, but you take the integral of theta, so there is no theta.
Oh, okay, okay.
Right?
But
There
like,
is no theta at all.
but
Okay.
basically because we don't care about theta, it means that something around any theta would kind of converge in a
Well, this is something you cannot say, unfortunately. This is something you cannot say. It has to be globally. You cannot see something around some point from this integral convergent. This is
but
so-called global quantity.
sorry, aren't we taking like the integral from minus pi to pi, right?
Yes,
And it's kind of like an area around C in a sense. And I think
but it's not really around t. Around t must be some very small interval, right? This
but
means
also,
oh,
if this integral goes to 0, I think we can also argue that by taking like smaller integrals with like less boundary, it still would go to 0.
no, unfortunately, no. It has to be the whole period, not locally,
Oh,
not
okay.
some one. This is very important. Okay. Any other question? Okay, so let's try to do some preparation or the preliminaries about these theorems, which probably I should, well, I hope you already have this kind of well, preparation by yourself because we assigned some kind of homework problems about it, which is the knowledge about the vector space. I hope you still remember what is a vector space by doing your homework. Okay, a vector space is actually from algebra, right? It's a set, and this set is closed under linear combination, linear operations, right? Which means it's closed under addition and closed under scalar multiplication or constant multiplication. If x and y and z in V, well, we have x plus y is in V, and cx is in V, and so on, right? This is the meaning of a vector space or a linear space. And well, of course, addition must satisfy some axioms, and this scalar multiplication must satisfy some axioms, and also the scalar field or where the constant you use to multiply could be on R, it could also be on C, right? So it's a vector space over R or over complex numbers, okay? So which means what kind of scalar you use to multiply it. And I hope you know what is a vector space. And I believe when you learn this vector space, you also learn what is the inner product on a vector space. We may have an inner product on it, let's say is something multiplied by another element, right? And it satisfies, say this multiplication satisfy ax plus byz is equals to axz plus byz. Okay, if it is over, let's first say it's over R, so that A, B are both in R, and this inner product will give you an operation and gives you result on R. It's a real number. Everything is just a real number. Okay, and so does x times ay plus bz is equals to a times xy plus b times xz. Okay, this is inner product on a vector space over R. And then based on this inner product, it can induce, so-called induced a norm on this inner on this vector space. Which is x, the norm of x is equals to x comma x with power half. Okay, this is this is a norm of x, and we say this we say this inner product is strictly positive definite if x equals to the norm of x equals to 0, if and only if x equals to 0. Okay, and also x comma x is greater or equal than 0, and this is 1, this is 2. So this means, well, if you have an inner product, of course, you want it, if it is in Rn, then you want it to be something like you use x multiplied by x, it's always non-negative. Okay, and if it is negative, it is 0 if and only if x equals to 0. Well, this may not always be true, right? You will definitely have some other kind of inner product on even on Rn, such that it's not strictly positive definite. For instance, if it is in R3, then ABC times DEF is equals to AD plus BE plus CF. This is the usual inner product on R3, right? But of course, you can equip R3 with another inner product. ABC times DEF is equals to, well, without the first term, BE plus CF. Okay, and you can check that this is still an inner product on R3. But for this inner product, it is not a strictly positive definite, because you can have 100 times 100, which equals to 0, but 100 is not equals to 0. It's not a 0 vector. Okay, so well, if you have this kind of inner product is strictly positive definite, then well, it is something a little bit better in some sense. Okay, we'll see why I say it is a little bit better. And this is something over R. Of course, over C, we can also have some kind of inner product. But over C, we have to be a little bit more careful about whether you choose, whether you take the conjugate or not. Over the complex number. If it is, for instance, let's say CD, C to the power D, then we see that, okay, Z is Z1 until ZD, which is in CD. and that means Z1, Zi are in C. Okay, all are complex numbers. And let's say W is W1 until WD. And then how can you define the inner product of this Z and W? Well, the most natural way to define the inner product would be, now, of course, you should multiply term by term, right? But if you choose multiply term by term, you find that if W equals to Z, then this multiplication, it cannot guarantee to be positive, right? So here you have to be careful. The inner product on the complex numbers, complex vector space should be Z1 multiplied by W1 bar instead of W1. And ZD WD bar. Okay, so that you can define this the norm of a vector on CD, so that it can coincide with C1, right? The norm of a complex number is just a Z times Z bar, right? The conjugate of Z. And this inner product is again strictly positive, definite. And moreover, it is, well, in R, this kind of inner product is symmetric, right? X times Y is equals to Y times X. But here, this inner product over C, it is so-called Hermitian. Hermitian. Well, instead of symmetric. Which is, if you have Z multiplied by W, you want to swap them, then what you have is W times Z with conjugate. Right? Because if you swap them, then this is W times Z1, W1 times Z1 bar, and so on, right? So which means if you swap them, then you should have a conjugate. Okay? And you can see that why we are interested in this kind of multiplication is simply because, well, we try to study the Fourier series, and the Fourier series is defined on the complex plane, right? It's complex numbers. All the coefficients are complex numbers. And also, by this, you can also get something different from this kind of distribution rule. That is, if you have alpha x plus beta y multiplied by z, yes, you still get alpha x times z plus beta times y z. But if you alpha beta is on this z side, x times alpha y plus beta z. What happens is if you try to take out this alpha and beta, instead of, well, alpha and beta, you should have the conjugate of alpha. X times y plus the conjugate of beta, y, well, x times z. Which is something very trivial. You can see that from here. If you have some numbers multiplied by w and you want to take it in front, then you have to have the conjugate instead of nothing. So this is the only difference. You have to be careful from this complex vector space and the real vector space. Okay, and the complex inner product and the real inner product. Okay, that okay? Any question?
Looks good.
Okay. Then what we have is, well, because later we will see some very general, well, vector space, which is different from Rn and Cn. So right now, we will assume something, we will try to find some general properties of the inner product of a vector space. or maybe sometimes if you have an inner product of a vector space, sometimes we also call it an inner product space. But let's say it's an inner product of a vector space. Let's say V is a vector space, and with inner product, say something multiplied by another thing, this inner product. It is very nature to assume that it is Hermitian or symmetric. But as you can see this example, we may not assume that all the inner product on a vector space is positive definite, right? So let's say we only have this inner product to be symmetric or Hermitian. Then, and with norm induced by this inner product to be this norm, okay? Then two elements, x and y, are orthogonal, which is the same as orthogonal in geometry. If x comma y is equals to 0, we write x is orthogonal to y. Then what we have is, even you don't have the positive definite property of your inner product, as long as it is Hermitian or symmetric, we will have this kind of properties about the inner product. These properties are just from geometry, which are very interesting, but I'm not pretty sure whether you have learned this in your 202 or not, so I'll just write it here and maybe prove some of them. The Pythagoras theorems. If x is orthogonal to y, then x plus y, the norm square of x plus y is equals to x norm plus y's norm. Okay, well, which seems to be trivial. You can just expand it, and that's all, right? A second one, the Cauchy-Schwarz inequality. This is one of the most important inequality in math, which is you have x multiplied by y. The absolute value of it can be bounded about by the norm of x times the norm of y. Okay. And the third one, the triangle inequality. Well, by the way, although we assume that it is not strictly positive definite, but we will still assume the inner product is positive definite. Okay, so x comma x is still non-negative. Otherwise, this norm doesn't make sense. Okay. This is so-called the semi-positive definite. The triangle inequality is also valid, which is x plus y is less or equal than x norm plus y's norm. Now you can see why we call it a triangle inequality, simply because if you have a vector, there's three vectors, this is x, this is y, then this is x plus y. Okay. So we have the Pythagoras theorems, we have the triangle inequality, we also have the Cauchy-Schwarz inequality with an arbitrary inner product. May not be positive definite. Okay? May not be strictly positive definite. I'm sorry. So that's proven. Okay? The first one is trivial, as I mentioned. This is just x plus y multiplied by x plus y. Then you can expand it, and x is perpendicular to y, x orthogonal to y. That simply means x, the cross term, just disappears. you have these two guys. Okay, so one is trivial. Let's try to prove two. How can you prove the Cauchy-Schwarz inequality? How can you prove the Cauchy-Schwarz inequality? Anybody tried that before?
Oh, I think induction works.
Well, but we don't know whether this vector space has its finite finite dimensional or not, right? This is in general. We don't even have a basis for this vector space. So let's try to prove it in this way, okay? First, let's say that if y's norm is equals to 0, okay? Because, well, what I want to do is I want to divide y's norm both sides and then try to see something. So if we want to divide it, then we should discuss whether y's norm equals to 0 or not. Suppose y's norm equals to 0. Be careful here. We cannot guarantee that y equals to 0 because it's not strictly positive definite. Okay. Suppose y's norm equals to 0. Let's look at this form: x plus ty's norm square. Okay. We know that this is greater or equals to 0. Right-hand side is already 0 if y's norm is 0, so we only need to show that the left-hand side x times y is also equals to 0. Then we are done. Then we are done in this case. So let's try to look at this form. This form we can expand it. Is equals to x norm square plus t times y's norm square, which disappear, plus, well, the real part, 2 times the real part of x times y. Right? Let's assume it's Hermitian. Let's assume it's Hermitian. Or if it is symmetric, then x times y is a real number. So yeah, it's also equals to 2 times x times y. Right? So you have this times this, well, times t. Greater or equal than 0 for arbitrary t. For either plus or minus t, right? X squared is a fixed number. And the real part of x times y is also a fixed number. Times t is always greater or equal than 0, so that means the real part of x times y must be equals to 0. Otherwise, it cannot be 0 for any t. Right? Similarly, let's consider I times t times y's norm square. It's still greater or equal than 0, but then now it equals to the x norm square plus 2 times the imaginary part of xy times t. Well, which means by the same argument, the imaginary part of this x and y equals to 0. That means x times y equals to 0. So the inequality becomes an equality, and we are done in this case. Right?
Wait, sorry.
Mm-hmm.
Why, when we're expanding x plus ty norm squared, how did we get that it's only the real part? Shouldn't it just be like a norm of
X plus ty, right? X plus ty, and this is equals to x squared plus t times x comma y plus t times y times x.
oh, and that I see.
This
and
is
that
Hermitian, so this 2 addition will give you the real part.
okay.
Okay. So we have this inner product of xy must equals to 0 if y's norm equals to 0. So now suppose y's norm is not equals to 0. Then let's do it this way, which is let's use x to subtract everything you project on y. Okay, This is a usual method when you're trying to find one. Well, if you gave me a basis of a vector space, then I can find a orthogonal basis based on this basis, right? This is so-called the Shor's method or Shor's algorithm. So let's try to use X to subtract some Y so that it orthogonal to Y. If you want it to be like that, then C must equals to X times Y divided by Y times Y, which is Y's norm squared, which is why we assume Y's norm is not equals to 0 is necessary. Then you can find that X times CY is orthogonal to Y. Okay? You subtract everything that parallel to Y, then every other thing will be perpendicular to Y. Then that means by this Pythagoras theorems, the X norm is equals to X minus CY's norm plus CY's norm squared. Because X is equals to X minus CY plus CY. And these two guys are orthogonal to each other, so you can split this X to these two parts. Okay? And this is something non-negative. C is equals to xy squared divided by y squared to the fourth. We get x squared times y squared is greater or equal than, well, x, y squared. So we prove the Cauchy inequality. Okay? Any question? And for the triangle inequality, it's well, it can be seen as a corollary to the Cauchy inequality, which I would like to leave it as an exercise for you to do. See, this one you take square, you want it to be less or equal than these two guys. And of course, that is true by the Cauchy inequality, right? Because you have the inner product terms that can be split into x times y as norms. Any question?
No.
Okay. So we show that without assuming that the vector space is Rn or Cn, we still have those Cauchy inequality or the Pythagoras theorems or the triangle inequality. Okay, this is very important. And then the reason why we don't want to involve the Rn is simply because we have some examples that are totally different from Rn. Let's see examples. For instance, this example. This is so-called the little L2 space over complex number. It's a vector space over complex number. Is the set of all two-sided infinite sequence of complex numbers. Say, well, a minus n, a minus 1, a 0, a 1, and a n, this kind of sequence. Okay? It somehow looks like C infinity, which is, well, you have infinite many, well, it has an infinite dimension, right? It has infinite basis, in some sense, basis. And it has, because it has infinite many terms for each element on it. Such that this little L2 simply means such that the summation of an square and in Z is less than infinity. It converges. You take the square of them of each coordinate or of each numbers and take the sum is less than infinity. Okay, this is so-called the little L2. Of course, you can also define what is little LP. That is, you change this 2 to be P. Okay. Now we have a space, and we haven't shown that it is actually a vector space, and we didn't tell you what is the inner product on it, and we don't even know whether it has an inner product or not. Okay. And before I say it is actually a linear space, maybe I should tell you, well, maybe I should say why it is a vector space at the very beginning, right? One can check that this is indeed a vector space. That is, well, if you have two vectors on this space, B in this L2Z, A plus B is in this L2 of Z. Of course, you have a complex number and multiply it, it's still in this little L2 space. But then the addition is not trivial to see why the addition is also on this little L2 space. Okay? Why A plus B is also on this little L2 space? Let me ask you why this is true. If this is true, then we are done. Then we say that, okay, this little L2 is actually a vector space. But then why A plus B is in L2, little L2?
Oh, because we can use the triangle inequality, and then because
we don't have anything like triangle inequality because we don't even have an inner product. We don't
oh
have
wait, I forgot we're doing. Wait, then I'm confused. So those ANs are complex numbers, right?
AN are complex numbers. This
Okay.
issue 2Z is just all these numbers such that the sequence of numbers such that AN square, if you take the summation, is less than infinity.
But then you can just say if you have like AN plus BN everywhere, like in those brackets, then their radius would be by triangle inequality less than radius of A plus radius of BN. And so
Well, you don't have anything like radius, right?
when I say radius, I mean like the modulo of the those are complex numbers, so we can use triangle inequality, right?
Well, triangle inequality is true for only finite many terms, right?
Oh.
Well, if you have infinite many numbers, how you can use triangle inequality?
But we're summing wait, so when you say A plus B, you mean that we take
we
A
want to do that term by term, yes?
Yeah, so we have term by term. So like in one term we have AI plus BI in the its value, like the norm, and it would be less than norm of AI plus norm of BI. And then when we write the sum of all of them, we just rearrange them so we get the...
Well, but that's not an analysis proof, right? You can say that for each single term, you have AI plus BI with square is less or equal than AI square plus BI square. That's okay. But if you try to say this by saying that the summation over all the I in Z is also less or equal than the summation of all the I in Z, you have to prove it, right? Because this summation is for infinite many numbers. This is something you have to make it clear. This is not something trivial, okay? Because if you do not have this kind of argument, for instance, you have two sequences, you add them up, then one sequence has an upper bound, the second sequence also have an upper bound. why it is true that the summation of these two sequences is less or equal than the upper bound of one plus upper bound of another one, right? So this is something you have to state very carefully by something we are able to prove, okay? Because you take this kind of thing infinite many times, and then take the summation. You should try to explain why this kind of thing is true. Well, I agree this is true, but this is not something you have learned, okay? Or maybe you can say that it is something you have learned, then you have to tell me in which textbook you have learned this property. In general, this might be something not trivial, I'll say.
Oh wait, can we take the kind of like a supremum of the series? Like,
Well, you could, but I think the easier way to state this kind of thing would be, well, how about we take the truncation? Let's say AN to be something like, well, you have a lot of zero, and only until capital N, you have something that's zero. Because what we're trying to do here is you try to, well, show that if you try to show that by this, this definition of the convergence, then what you're trying to show is, okay, the summation I from minus n to n is, has an upper bound, right? It has an upper bound. Then what you can show is, then you if everything is bounded about by some constant, then take n goes to infinity, you can get this kind of thing. Okay? So which means if you try to make this argument clear, what you have to do is you have to make it a finite many terms and use a triangle inequality instead of using this triangle inequality for infinite many terms and take the sum, because that's something you don't really know. Okay, if you take this kind of truncation, what you have is an plus bn. Then you can say that by triangle inequality, well, an is actually equals to this, well, let's say this kind of norms is just an plus bn. You take the norm and you take square and n from minus n to n. Here you can say that it's less or equal than, yeah, maybe you should take the half power of it. And then this kind of thing is less or equal than, by whatever triangle inequality, is less or equal than the norm of an squared plus the norm of bn squared. Okay, and you're right, then we can take the supremum because, well, this is less or equal than a plus b. The summation of each term square, and you take the half power, plus the summation of these terms, you take the half power. Okay, so if you take n goes to infinity, you get a plus b is less or equal than a plus b. So which means if you define this kind of summation as a norm of it, as a norm of a vector on this little L2, this norm satisfies this well, triangle inequality. And moreover, you have shown that it is actually a vector space. Okay, so this gives us a hint about how you can define the inner product on this little L2 space. Let's say A is an, and from minus infinity to infinity, B is bn, and from minus infinity to infinity, as a sequence of numbers, then A times B should be written as a summation an bn bar. Just like Cn, just like in the complex n-dimensional space, right? You should define it this way. Then you can see that this kind of inner product, it induces the norm of A, which is A multiplied by A, you take the half power. And this is, well, this is inner product of little L2 of Z is strictly positive definite. Okay, which is easy to see. So we do have a vector space which equipped an inner product. And this inner product is strictly positive definite inner product. We have this little L2 and it has an inner product. Moreover, this would be something in your homework. This will be a homework problem, again with some hint. Well, the vector space is complete. This vector space is also complete, which is L2, little L2Z is complete. That is, we have the norm on this vector space, right? We have the norm on this vector space, then we can define what is a Cauchy sequence. What is a Cauchy sequence of this vector space? Every Cauchy sequence. What is the meaning of Cauchy sequence? In the norm, converge to a limit in little L2 of Z. Okay. By the way, what's the meaning of a Cauchy sequence? A sequence is Cauchy sequence if
there exists, like for any epsilon, there exists such n that anything that's bigger, like the pair was distance between them is less than epsilon.
That's right. So every later terms have the difference less than epsilon, right? If you choose the later terms to be later enough. This is the meaning of Cauchy sequence. But this Cauchy sequence may not have a limit. For instance, the Cauchy sequence on the rational numbers may not have a limit because the limit of the rational number could be something like a rational number. The rational numbers could be a real number, could be an irrational number, right? But here we say that this little L2 is a complete vector space, which means all the Cauchy sequence will have a limit. It will have a limit on this little L2 space. It will converge to something, and this something will be on this little L2 space. And this would be a homework problem for this week, okay? And of course, we will have some hint on this problem. Which means this little L2 space is more or less like the real numbers, not really like the rational numbers. Okay? Okay.
Wait, when you say that the inner product is positive definite, you mean that like the inner product of like A with itself, right? Because
yes, A with itself is greater or equal than 0, is equal to 0 if and only if A is 0.
Okay. Because
This
like
is
other
meaning of,
products can be negative, right?
It cannot be, well, of course, if x times y, it can be negative. Yeah.
Okay.
If you have two numbers multiplied together, it could be negative, it could be positive. Okay, but if it is a number times itself, it has to be non-negative. And here, strictly positive definite means, well, if a number times itself is equal to 0, then it must equal to 0. Okay. This is one example. Little L2 space is one example. Another example is, well, let's say, oh, by the way, there's one thing I forgot to mention. This is something we may not use in this this course. This is something that's quite important in functional analysis. An inner product space with these two propositions, which means this inner product is strictly positive definite, and this vector space with this inner product induce a norm, and with this norm is complete, is called Hilbert space. A Hilbert space, which basically means complete the inner product space. Okay, if any of these two conditions will false on this inner product space, then it is so-called the pre-Hilbert space. Well, in functional analysis or in the future, you will always see something to be a pre-Hilbert space simply because it's filled as a completion. Okay, it may not be complete, so that it becomes a pre-Hilbert space, and then you try to make the completion of this space. But basically, if an inner product space is it has a strictly positive definite inner product, and it has complete. It is actually complete. Then it is a Hilbert space. Okay. Just a name at this moment. It's just a name, nothing more than that. And another example is so-called the Riemann integrable function. The set of complex valued Riemann integrable function. On minus pi 2 pi over R. Well, over C, I'm sorry. This is, I'm sorry, this is another vector space. You see, again, this is a vector space, not finitely dimensional. Okay? This is first a vector space. For sure, right? You have two functions that is integrable, the addition is still integrable. Okay? And we can define the inner product of two functions to be something like this. And F times G bar d theta. Okay? And the norm of F is equals to, well, if it is like this, if you define the inner product like this, from minus pi to pi F squared d theta with half power. You see, naturally, we need to define this kind of inner product on this Riemann integrable function space to be something like this. Okay? And if you are interested, you can try to check by some other method why this is a very good thing, or why the Cauchy-Schwarz inequality is valid in this, on this inner product space, on this inner product. Of course, you can prove it by our method, because our method definitely works on this case, but you can also check what does it mean for the Cauchy-Schwarz inequality on this norm. Okay? And this norm, well, on R, unfortunately, is not positive definite or strictly positive definite. Why is that? Why this norm on R is not strictly positive definite? What's the meaning of that? Any idea? Why not strictly positive definite if you define the norm like this?
Wait, because I don't know, kind of. Because we can have like periodic functions, and they can sometimes cancel themselves out just because they're periodic.
But this kind of thing equals to 0, right? It cannot cancel, actually. It is positive or not negative. Then why we say that it's not strictly positive definite?
Well, like say for example, if we have like some kind of a function with period 2 pi, then f pi square, like say that f big is an integral of f small, then we can sometimes get that f pi minus f minus pi would kind of cancel each other out because they can be periodic sometimes.
Well, I don't think that is a good reason, right? Because you see, for this one, if you learn this well, integrability of a function, then you know that if it has a lower bound, right, then the whole thing also have a lower bound. So there is no cancellation at all because the integrand is actually non-negative. Okay. But then why we say that it is not strictly positive definite? What's the meaning of not strictly positive definite?
It means that sometimes we can get 0 even if f theta is not 0.
Yes. Why is that?
Oh wait, what if we have that f is strictly imaginary? No, but then
Well, even if it is strictly imaginary, then we take the norm, it's still something non-negative, right? Any idea? Well, I think you have mentioned this before, Aya. We have some function, right? Even if it equals to 0, this integral equals to 0, we can still change some values at some single point, right? We could have some function such that it's equals to 1 if x is equals to 0, is equals to 0 if x is not equals to 0. What is the integral of this function square? What is the integral of this? What is the integral of this?
oh, it's still 0.
It's still 0 because it's only at one point equals to 1. This point is a removable discontinuity, right? So it's still 0. But this function is not 0, right? So it's not strictly positive definite. And moreover, well, this space, this R, is not only not strictly positive definite, it's not even complete. Okay? As, well, you may have some function which, well, if it is theta equals to 0, it's equals to 0. Theta is not equals to 0, then theta is equals to log 1 over theta. This theta is greater than, is not equals to 0. Maybe I should say that's value of theta. Then we can define fn theta is equals to 0 and f theta when theta is between my 1 over n to 0 and theta is between 1 over n to pi, which means your f theta is something like this. Then your fn theta is nothing but you do a cutoff during 1/n and take the rest part to be your f theta, to be your fn theta. Okay, you can find that. You can prove by yourself. Fn forms a Cauchy sequence under this, well, inner product, under this norm. And however, the limit of Fn, well, should equals to f theta. If it exists, it must equals to f theta pointwisely. But Fn of theta, well, does not have a limit on the integrable function because this function is not in the Riemann integrable function, the set of Riemann integrable function. Okay, so which means this Riemann integrable function set is not even complete. Which means this inner product is really a bad inner product. It's not strictly positive definite. It's not even complete. So again, later, if you learn the measure theory or the real analysis, you will learn how we can fix it and how we can, instead of the Riemann integrable function, we define what is a Lebesgue integrable function, and then in that space, we can somehow fix these two problems and make some kind of vector, well, some kind of inner product, complete, strictly positive inner product. Okay? Any question? Any question? Now, we are able to prove our theorems 1. You may find nothing from our introducing of this vector space language, which can be related to this kind of theorems. This will square convergent theorems. You may find nothing relevant to this one. However, I will use the vector space language to prove this. Okay, let me prove it. Well, you can see that. Let's consider all the Riemann integrable function R. Okay, all the Riemann integrable function space R. And we define f multiplied by g is 1/2 pi minus pi to pi f g bar d theta. And let's denote this E n theta will be e to the I n theta. Okay. What we conclude is this En is also, it's not only orthogonal but also orthonormal. That is, En times En is equals to, well, I use this chronic delta, this notation, Mn, which equals to 1 if M equals to n equals to 0 if M not equals to n. This is just a notation. It is 1 if M equals to n, if it is 0 if M not equals to n. Okay? The multiplication, the inner product of Em and En is this delta Mn. Okay? Which is something we have shown, which is something very easy to see. And we find that this kind of functions, e to the in theta, forms an orthonormal set. You can imagine, well, whether it is a basis or not. However, if you try to say something about basis for infinite dimensional vector space, well, there are different kind of definition of basis. So right now, we only say that it is a orthonormal set. Okay. Any question? Okay, now what we also know is, well, the inner product of F and En is what? Is An, right? Or F hat n. So now we use our inner product language to present everything we have before, okay? This is just the inner product of F and En, which looks like a basis. Then what is Sn of F? Sn of F is the summation as n less or equal to n, Ane. Looks like the linear combination of bases. Not really, but really looks like. Is orthogonal. Well, I'm sorry. And if you have F, subtract this Sn of F, which is F subtract n less or equal to n, A-N-E-N, you use F subtract all the projection of F on En. All the projection component of F on En, we know that it's orthogonal to En for n is less or equal than n, right? If you use En multiply it, it will give you 0. Okay? So we have F minus the summation n is less or equal than n, A-N-E-N. This guy is perpendicular to the summation of n is less or equal than n, some b and e, any b in C. You can do a linear combination and it's still perpendicular to this one. Okay. So by using the language of this orthogonal or the vector space, what we have is F is equals to F subtract this partial sum of F and plus this partial sum of F of E and A and E. So by Pythagoras theorems, the norm of F is equals to the norm of this guy plus the norm of this guy. With square, I'm sorry. Okay. That clear?
Yep.
This is just like a linear algebra, right? Nothing but a linear algebra. Moreover, what is the norm of this square? It's the inner product of it and itself, right? But we know that if you do the inner product, the only thing left would be, well, the only thing left would be An times En times An times En. Any other term, if you expand it, will disappear, right? So which means the norm of this kind of thing is just the norm of An squared, which is just like the vector. If you do a decomposition of a vector with respect to a orthonormal basis, then the norm of this vector is equals to the norm of all the coefficients, and you take the sum. Okay? So that means your F's norm is equals to this guy's norm square plus the summation of An square as n is less or equal to n. Okay. Well, So it seems that if we want to show this term tends to 0, we only want to show that if you have this, all the Fourier coefficients square, you take the sum, it's equals to the sum of the norm of f, which is an integral. Then let's try to, well, prove it by this way, but it seems that it's very hard. So there is another way to get rid of these terms, or we'll get this term tends to 0, which we will use a lemma. This lemma is some kind of best approximation lemma, which says that if f is integrable, let's say an is equals to f hat of n, then f minus Sn of f, you take this kind of norm, this integrable space norm, and it's less or equal than f, subtract n is less or equal than n, some Cn times E. Which means this kind of approximation, in the sense of mean square, is the best approximation. The equality holds if and only if when Cn equals to An. So the Fourier coefficient or the Fourier series can approximate f by this kind of mean square means to be, well, faster than any other kind of trigonometry polynomials. Okay? Any question about this lemma? Then, well, let's postpone the proof of this lemma slightly later. Suppose we have this lemma. We are done, right? We are almost done because, well, why is that? For epsilon greater than 0, there exists a trigonometry polynomial P, right, of degree, because we know that the fair kernel is a good kernel. So we can always find the trigonometry polynomial to approximate your function uniformly, right? For continuous function, f theta minus p theta is less than epsilon for any theta. Okay, if this f is continuous. So that means, okay, this f minus Sn of f is less or equal than f minus f theta minus p theta. Because p theta, whatever it is just some polynomial. It's just some trigonometry polynomial, which is less than epsilon. Okay? Whenever n is greater or equal than m. It's a better approximation than some other trigonometry polynomial. So this is true for continuous function. Now, for integrable function, if f is only integral, then we can use our approximation lemma that we used before. Any integrable function can be approximated by continuous function, well, in the integral way, right? Then there exists some g such that g, well, the supremum of g is less or equal than the supremum of f. and let's say it's less or equal than b, and we know that g minus f, if you take the integral, is less than, say, epsilon squared. Okay. You can use g to approximate f. With this g continuous. Okay. So this means the integral from minus pi to pi, well, f minus g square, which is f minus g, the norm square, is equals to 1 over 2 pi f minus g square d theta is less or equal than some constant, because this is f minus g times f minus g. F minus g is bounded about by 2 of this b. So it's 2b over 2 pi minus pi to pi f minus g d theta. It's less than some constant times epsilon squared. So f times p, the trigonometry polynomial, is less or equal than by triangle inequality f minus g, which tends to 0, less or equal than epsilon, g minus p. If you choose your p to be approximation of g, it can be less or equal than epsilon as well, C1 and C2. So that means you still get f minus Sn of f tends to 0. Okay. So now we finish the proof, except we need to show this best approximation level. So this we will continue on Thursday to prove it. Okay, to finish or to close our proof. Okay, that's all for today. And if you have any questions, feel free to ask. Otherwise, feel free to go. Okay, I'll be here until 6.
Hey, can I ask a question, or maybe
Of course.
Right. So, the page 39 to 40, we were trying to prove that if f is an integrable function, blah, 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 then f theta is equals to 0 whenever f is continuous. And so, prove it, would it seem a bit of a weird trick when we found trigonometric?
Yes, this is a very technical proof, and but if you could understand it, that would be good, because this is also a very standard analysis proof. But if you don't, that's also fine, because it's kind of tricky.
Okay, and I read through it and I understand most of it. The only thing is that I was kind of not sure. So basically, they say we want to take PKs, which are trigonometric polynomials. So basically, like PK has a form of e in the power of ikx, or
something like that. Yes.
Okay, so they take those and they want them to pick at 0, but then basically they start choosing some kind of p theta, which is
like this, right?
minus t plus epsilon. And so I'm not really sure, like, so did they just define a completely random function they wanted? Because I don't really know where they're getting that from, because that's not how.
Well, you see, he tried to define p theta to be epsilon plus cosine theta, right? So, well, this kind of thing is somehow has a peak at theta equals to 0, okay? But then he tried to take the case power of it. If you try to take the case power of it, then it will still be 1 plus epsilon at the theta equals to 0, right? But if cosine theta is less than 1, if for other point, it will disappear very soon, because if you k goes to infinity, for any number that is less than 1, it will disappear.
Yeah, I mean, I
Which is a
understand.
picture. Mhm.
I understand what, like, that he, like, why does he take the powers? I'm
Mhm.
just not really sure if, so basically, why would pk at the same time be a trigonometric function and at the same time be the power of p theta?
Well, what is a trigonometry function? Trigonometry function is a function formed by cosine theta, sine theta, and it itself is a polynomial, right?
Uh-huh.
So of course, this is a polynomial, right? It is a polynomial of cosine theta.
Yeah, but we also have an epsilon there. So do we just show that
Epsilon
we
is a
can?
number, right?
Yeah.
Epsilon is a number. If you have a polynomial, then of course this polynomial could have a constant term.
Oh, so trigonometric functions can have constant terms.
Yeah, it's just a trigonometry polynomial, right? It's just a polynomial.
Okay, because then I was thinking, oh, then it makes sense why they're different from Fourier coefficients, because I couldn't
Yes,
make the differences. Okay,
exactly.
then that really started to make sense. And um, dun, 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 dun. And then at the page 41, there's a corollary 2.3. And
Which page?
41.
41? This one? This one? Right?
Yeah. And
Okay.
they do the last corollary on that page, and they're trying to show that if f is continuous, and if the Fourier series are absolutely convergent, that Fourier series converges uniformly to f. And I understand how they show that it converges, but I don't know how they show it converges to the uniformly.
Oh, because you see, each terms has an upper bound, right? Each terms of the Fourier series has an upper bound, the norm of f hat. The norm of f hat n, right? And if you have this norm of f hat n is converge, then that means this sequence or this series it converge uniformly, right? By this comparison principle or by the properties or the criteria I just tell you when we discuss about this. When we discuss about this uniform convergence. How one sequence or one series converge uniformly, as long as you can find an upper bound for each terms and you take a sum, the sum of this upper bound just converge, then that means this sequence converge uniformly.
Okay.
Right? You try to remind this, maybe. See, if you have a sequence, you want to see whether the sequence converge uniformly or not. You just need to find for each terms, you find an upper bound, Bn. If Bn is summable, then An converge uniformly.
So if the function converges uniformly?
Well, this upper bound converge uniformly, converge absolutely. Then this series of functions converge uniformly.
For partials. Okay. Oh, okay. And then that page I have a lot of questions. So basically, when they are doing the proof, they write, moreover, the Fourier coefficients of G are precisely f hat n,
since we interchange the infinite sum with the integral. And I don't really see where they do that. Did they mean that they interchange infinite sums with the limit? Because that would make sense. Or
Which interchange? Which interchange?
like page 42, right after the
Yes.
formula,
Mhm.
like the continuation of that corollary.
Yes.
So basically they say the function g is continuous on the circle, and then
Yes.
are trying to show that Fourier coefficients of g are also the Fourier coefficients of f hat n,
Yes. Yes.
and
It's
how
simply because this convergent is uniform convergent, right? So if you try to compute the Fourier coefficient of g, what did you do? You try to multiply e to the minus in theta and take the integral, right? And it is a uniform convergent, so that means you can switch the integral and the summation. These two you can switch.
oh
And
okay.
then the only thing that left would be fn hat must be equals to gn hat, right?
Okay, so because converges uniformly change. Okay, and then dun. What dun. And oh, actually, I think some of the questions I understand now.
Okay.
Oh yeah, I didn't. So they were talking about belonging to the class CK or satisfying a Holder condition are two possible ways to describe the smoothness of a function. And why is that true?
Which one is, why is that
It's
true?
page 44, like,
Yeah. Okay. Mhm.
and so they, like, before the part with convolutions, like the last sentence, they talk about like how CK and Holder are kind of ways to determine smoothness, but like why?
Well, it's just because for this CK, it means how many times it is differentiable, right? For Holder, that means it's slightly better than this than continuity, right? For instance, if it is Holder of order alpha, C alpha, sometimes it's called C alpha, then if it is C1, then that means this for instance, this F is almost differentiable, right? Because if you divide this t by power 1, then f theta plus t minus f theta divided by t is almost have an upper bound, so that means it's almost saying that it's differential.
Oh, okay.
If you have some alpha here, then that means it's slightly less than C1. It's slightly less than differential, but it's still somehow better than continuous. Right? It's still uniform continuous. It's, right? So which is why you can define this Holder condition to as some medium case of this between this continuous and differential.
Okay, got it. And then, oh, okay. And then on the page 46, when they do all those weird equations, like inequalities, they write that the difference of two convolutions for x1 and x2 is less than equal than, and then they just basically open the brackets. So why is it less or equal? Isn't it just equals to?
Well, this is well, sometimes we don't really need whether it's equal or less or equal, right? Sometimes less or equal to is good enough, especially this kind of thing. For instance, if you take this absolute value inside, right? The absolute value inside, then this must be inequality. So which means it must be inequality. So which means we can put everything just less or equal to instead of equal.
Okay.
Okay. Let me stop the recording.